All right, so our next example that I want to look at, I think it's number 3. I want to look at the indefinite integral of tangent of x dx. And so let's just go ahead and nip something in the bud that comes up. People sometimes say, well, I don't really see any composition here at all, actually. So maybe I'll do u equals x. Well, that's fine. So if u is x, then du is dx. And so your original integral becomes the integral of tangent of u du. But you should realize that's true, but I haven't gained anything. This is one of those things that's not technically incorrect, but it's useless. So we're not going to ever set u equal to x simply because it doesn't do anything for us. So I'm sort of stuck, but I'm going to write this as the integral of the sine of x over the cosine of x dx. And now I'm going to think a little bit. So if I set u equal to the top, that's never going to work because, for example, u equals sine of x, then du is cosine, and I have a cosine, but you need to be able to factor cosine of x out upstairs. Du has to be upstairs. This cosine of x is downstairs, so that's not going to be the right substitution. But if we go the other way and we try u equals cosine of x, then du is minus sine of x dx. So then what? Let's write dx equals du over the minus sine of x. And so we can try to make the switch. This is going to equal what? I'm going to see a sine of x over a u, and then dx becomes du over minus sine of x. So you can cancel those, and you just get negative integral 1 over u du. Hopefully you remember this one. This one is just negative ln of the absolute value of u. We studied that back in chapter 4. What's the antiderivative of 1 over u? It's ln absolute value of u. Don't forget your constant, plus c. And then you ask yourself, okay, what's u? So this is negative ln of the absolute value of cosine of x plus c. But if you look this up in your book, you won't see this written down. And the reason is people don't like this negative sign dangling loose. So they pull the negative sign inside the natural log. When you pull it in, it becomes the power on this. You get this to the negative 1, which just flips this downstairs. But 1 over cosine is secant. So this is actually ln of the absolute value of the secant of x plus c. And that's what you'll see. This is one that you actually want to know. So Dixon is going to expect you to know this next semester in Calc 2. The integral of tangent x dx is natural log of the absolute value of secant of x plus c. So that's one to stick in your back pocket. You'll need it, trust me. Let's do one more, and then we'll break up this video. So I wanted to show you how you can actually work out, I think we're on example number 4, how you can work out definite integrals using U substitution. So let's work out this integral, the integral from 1 to e of the natural log of x over x dx. And so one way to do it is just ignore the bounds and focus on the indefinite integral. So we want to look at the indefinite integral of ln of x over x. I need to find an antiderivative of this function, of this function, right, the inside. If I can find an antiderivative of this guy, then I can go back and use it to evaluate that one. So I'm looking for a U substitution here. You won't, it's difficult to see function composition here, but if you notice that, hey, if I set u equal to ln of x, then du is 1 over x dx. So what? Dx is just x du. And now I can clean this up and say, okay, so this becomes integral. Ln of x is u over x, and dx is x du. The x's cancel, thank goodness, and so I just get the integral of u du. We learned how to do this in chapter 4. This is just u squared over 2 plus c, but what was u? U was ln of x, and so I get ln of x all squared over 2 plus c. Now I want to go back to my original problem. Let's copy it down. So we'll just copy. And I'm going to say, let's say, so this problem is just ln of x squared over 2 evaluated from 1 to e. You just plug the bounds into the antiderivative, and so you get what, ln of e squared over 2 minus ln of 1 squared over 2. Ln of e is just 1, ln of 1 is 0, so this one is gone. This is just 1 squared is 1, so you just get 1/2. So you can evaluate definite integrals as well using U substitution. Let me show you another way that you can actually do this one. So this is just a matter of notation. Some people like it, some people don't. If you wanted, you could actually do the U substitution. I'm going to redo it real quick. So I have the integral from 1 to e of ln of x over x dx, and I'm going to set u equal to ln of x. I'm going to set du is 1 over x dx. And so, of course, same thing, dx is x du. But now I'm going to go ahead and I'm going to change the bounds. So these bounds were in terms of x. That's what the dx is telling you. So you actually plug those into x in your formula for u. So this becomes the integral from ln of 1 to ln of e. You're plugging these bounds into your into x in the formula for u. And then just like before, you're going to get a u du. Well, ln of e is 1, so you get the integral from 0 to 1 of u du, which is just u squared over 2 evaluated from 0 to 1, which is just 1/2. So if you switch the bounds like I just did, then you don't have to try to come back. Once you switch the bounds, you're entirely in terms of u, and you just plug in those new bounds and you get out 1/2 just like we did before. So that's one way you can do this. Here's another way students like to work this same problem out. Another way students will work this out, and this is fine if you want to do it, is you can do this again right here. Let's just copy this. And so they'll do that, and then they'll say, okay, I'm going to write this as an integral again, and I'm going to have it's going to be u du, but I'm just going to put slashes where the bounds go to show that the bounds have changed. What you don't want to do, what's wrong, is to write 1 to e of u du. That's incorrect, and I will take off points if you do that, because that's not true. But if you want to maintain the fact that this is a definite integral, but you don't want to plug the bounds in and switch them, just put dashes. And so then you're going to get u squared over 2 evaluated, put dashes again, and then you plug in u, and you get ln of x squared over 2, and then you come back with the old bounds just like we did. That's fine. So the big takeaway here, what's wrong would be to keep the old bounds from 1 to e when you've got this thing in terms of u. You don't want to do that. Either leave them off or put dashes or switch them. And I'm not going to insist on any one of these. I just do insist that you don't keep the old bounds when in fact you should be changing them. So I'll stop this video here, and then in the next one we'll just keep going. I'm just going to do a bunch of examples with you.